Thank you. This is the Classic Literature and History Conference, correct? Am I in the right place? All right. No, I promise I'm not going to do a big, long history thing here, but there's just some interesting, some parallels, I think, that we can draw upon as we're thinking about securing our OT assets. So, over the course of history, there were three primary occasions when Rome was sacked. Beginning in 387, when the Gauls were the first successful one after the creation of the Roman Empire to sack Rome. The one that is kind of generally acknowledged as the end of the Western Roman Empire was in actually, it says 475, but it was in 476, the Ostrogoths. Now, the Eastern Empire lived on for many, many years after that, many hundreds of years, but that is generally the end of, the Roman Empire. So, I almost went the wrong way. Here we go. So, what the heck has that got to do with control system cybersecurity? Well, first, let's talk about how Rome kind of went and how it became to be. Rome started as a small city-state. And through a series of one might call mergers and acquisitions, it grew substantially. And it became, maybe till this day, the most multicultural society in the world. By the time of its fall, there were people from all over the empire doing all kinds of different things, speaking different languages and different cultures. Similar societies never happened again until many hundreds of years later. Think about industrial control systems. They started with one little computer doing some stuff over time. And organically, this thing has just grown. One last thing about Rome is that ultimately, while it grew to be that big, essentially, it just became overstretched. It just was not sustainable in regards to a government structure. Similarly, OT. It all began, we used to have pneumatic control panels, then came in digital control, and then it just grew over time. Basic process control systems and safety systems and PLCs and optimizers, and all that stuff has oftentimes been put at a plant that's been there for 40, 50, 60 years. It's very common. You walk into a plant and the basic process control system is literally 40 years old, talking to an optimizer that might be put in last week. And so it's this very diverse atmosphere. It's getting worse. IIoT, IoT convergence, let's put in more sensors and get all kinds of information. The business is demanding more data from these systems to manage the business. Just like the Roman Empire, I submit, as we're trying to protect these systems, we're getting overstretched. The second thing is, why did they attack in the first place? Why was it sacked? Main reason, it was there. Those first attacks on Rome were not about destroying Rome. It was about basically taking it over for its riches. At the time when the Gauls first invaded and successfully sacked Rome, by that time in the empire, the way secession happened between emperors was two or three guys would say, I'm the emperor, and whoever had the strongest legions won. Those legions had all kinds of people from all over the empire. Ultimately, people said, wait a minute here, why should I just sit by for this? I got a better legion than they do. Let's go. I'll take this thing over. So ultimately, it was a big, fat, meaty prize full of riches. It was there. And so ultimately, it led to its downfall. Well, let's think about critical infrastructure. CISA has defined 16 industries as critical to the well-being of our society, from food and agriculture and energy and dams, et cetera. I'm not going to list them all here. That is a big, fat, overextended, juicy target. Whether it be from nation states trying to disrupt society for whatever purposes, certainly criminal enterprises have realized I can make a heck of a lot more money sticking ransomware on these systems than grandma's PC. And so these are big, fat, juicy targets that are frankly under attack. And so just like Rome, we have very overextended systems that grew over time. We also have a very meaty target. So, what do we do? What do we do? Ultimately, I believe that in order to get cybersecurity to the right place, we really have to focus on resiliency. What does resiliency mean? Basically, resiliency is the recognition you're going to get punched in the face. And how well can you recover? these systems will be attacked. It's going to happen. The question is, can you take the punch? Can you react to it? Can you minimize the downtime? And can you get back up off the map and recover? And that's ultimately what we have to do from a security perspective. I want to talk more about that as we go through the rest of the presentation. So certainly there are challenges. And if you've been coming to this conference for a number of years, as I have, none of these things that are challenges to cybersecurity are new. Some we've made some progress on, some we haven't. How many years have we been talking about we have to get a good inventory? Dale talked about our first time, this morning in his keynote. We're still talking about we need a better inventory, and I completely agree, but ultimately it's still a challenge for us. Understanding how to do vulnerabilities. We all know you can't patch everything in OT and all those issues out there. We still haven't solved that problem. Managing the configuration of these devices is a big challenge. I'm going to talk more about that a little bit later, but at the end of the day, all this is about risk. It's about risk management and getting our security to the point where we feel comfortable. Yep, I can operate these facilities. I've reduced the risk to an acceptable level. We cannot take the risk to zero, although actually we can. I do have a solution. I can 100% solve the OT cybersecurity problem without shutting the plants down. We rip out digital control and we go back to panel boards. I promise you, they are not hackable. Now, screwdrivers and crescent wrenches will kill you. I've made a lot of mistakes with those way, way, way back in the day, but my point is I'm joking here. We're not going back to that. So we're going to have to manage this risk. There's a chip, monitoring a process, someone can get to it, there's a potential problem. So let's talk a little bit more about risk and what that means from an OT security perspective. Well, simply, risk is equal to likelihood times consequence. The higher those two factors are, the more risk that you are going to have. On the likelihood side, things like the vulnerabilities that exist on the network, what threats may be either lurking or potentially lurking out there, what vulnerabilities currently are known to be exploited, what is connectivity, zones and conduits and coming out, and then ultimately, always, the weakest link is the people. Someone clicking on the wrong email, doing the wrong thing, setting up the wrong configuration. These are always factors, and they all increase the probability of an attack. Consequence. So if someone gets in, they do something, what bad things can happen? That is consequence. Things like, if we're lucky, unplanned downtime. That's not good, but it's not the worst possible thing. Equipment damage. Safety incidents, brand reputation, having to pay the darn ransom. These are all potential consequences from a successful cyber attack. What I submit is that I believe as an industry, we have focused more on the likelihood side of the equation than on the consequence side of the equation. But it is a factor. And at some point, we better address the consequence side and make sure we can reduce the consequences associated with cyber attacks if we're going to continue making risk, getting risk to an acceptable level. So, at the end of the day, you're not going to protect your way out of this cybersecurity issue. It's just not going to happen. There's just way too many things that can happen. We can minimize it, but at the end of the day, we're going to have to be able to better improve our resiliency and reduce the consequence side of the equation. So, the Gauls are at the gate. They're attacking. They're having at it. What the heck are we going to do about it? Well, you know what? On that wall, you have a multi-function team. I got pikemen. I got guys with swords. I got archers. I got guys pulling boiling pitch. I've got a multi-functioned team to repel the attackers. Same thing if we're dealing with a security incident. I better have a multifunctional team to deal with this. Certainly, I need security professionals. People understand, how people attack and what they do. I need people that understand the networks and how things are there and how things are designed. IT professionals. But I'm going to talk about this quite a bit more. If you don't have a control engineer on that wall with you, you're going to have a problem. We'll talk more about that. We're going to get very specific here shortly in a real type of scenario for an attack. What do they need to do their job? If they're just up there with their different teams, they need their bows and arrows and everything else. What do they need to do this job? Well, first and foremost, they better have been trained. how to respond to an attack. Who do I call? Who gets up on that wall? What do we do? And they should have gone through tabletop exercises to make sure that we are prepared. We've been trained. We're good to go. The Army's been trained, not just pulled out of bed and here's your sword, go fight. They need other tools as well, though. Certainly they're going to have network traffic analysis so we can figure out what's been going on within the networks. I know all the event data that may have flowed before, during, and after the attack. I better have network maps and an inventory, that word again, of all the stuff that is out there so I can know where things may be. I need the vulnerability information in regards to, wait a minute here, these vulnerabilities exist. It could be they're attacking this and get after different ways. I should have some good threat intelligence. Hey, this looks similar to things that have happened over here. But also, very important is you need, and this is where the control engineer comes in, detailed configuration information and forensic change analysis. I'm going to show you an example here of how an attack can lead to really bad things by getting the configuration of that device. Finally, the worst case scenario, really bad, whether it be ransomware or gosh, thing has gone too far, I need a trusted restore point. And let me tell you what I mean by that. Trusted restore point is not a backup. Control systems are not like a computer where I can, ghost it, put it on the shelf, oop, not good, wipe it clean, put it back on. Control systems don't work that way. Oftentimes there isn't a backup, you can just load and go. Before you turn it on, there could have been changes made that, oh my gosh, I can cause a real problem. If I turn the key and turn that plant on, that could cause a real problem. You need a very detailed, here's the configuration before, here's the configuration after. Will this plant operate properly through that startup to make sure, yep, I can do this thing. So backup and recovery in the traditional sense doesn't work in OT. Trusted restore point with a complete understanding of the configuration, and is it the right configuration for startup, is critical to improving resiliency to make sure that I can recover from the punch that we just took. So let me look at this in a bit more detail. I'm going to walk you through an example. This is a typical process. This is an ethylene cracking furnace. Ethylene is the basic building block for many of the plastics that are in this room today. That ultimately leads to polyethylene. How do you make ethylene? Well, basically what you do is you have a furnace. What is a furnace? It's a big, giant box of fire. That box of fire is fed through fuel and inlet air at the bottom to heat up that furnace. On the inside of that furnace are a big set of tubes. Those inlets includes the hydrocarbon feed. It could be ethane or other things that you're going to use. There's different ways to make ethylene. And steam. What happens is that you mix basically the hydrocarbon and steam, you heat it up like crazy and the chemical reaction takes place. A couple interesting things about this. Number one is that you think about these tubes that are in there where this is basically rushing through, okay? At the end of the day, what's coming out of the back end is hydrocarbon that's at 1,400 degrees Fahrenheit. If anyone can tell me how to make this process 100% safe, I'm looking forward to hearing it. It is inherently risky to make ethylene. Second thing, where that stuff, those tubes, where the hydrocarbon is going through, it's basically a little thin wall of metal. Why is that? Well, let's make a thicker tube. The reason I want to do that is this reaction is highly endothermic. What that means is I need a lot of heat getting in to make the reaction happen. Where's that heat come from? That's fire going against those tubes to make this thing really, really, really hot. If you overheat those tubes, they fail. How do you keep the tubes cold enough? You shove enough hydrocarbon through, which is the cooling agent, while it's going through its reaction. That's what keeps it cool enough. If you slow down the flow too much, the tubes could potentially fail. You could also get bad product and everything else. So my point is that essentially, how do you make ethylene? You essentially have a controlled bomb and make sure it doesn't explode and pop ethylene out of the back end. Okay? That's what it is. All right? So let's talk a little bit, oh gosh, and then there's all the control constraints. You got to balance the fuel-air ratio and a lot of constraints you have to manage. Make sure you're not making too many other products. If you leave the resident time too long, you make the wrong stuff. Let's not get into all that. So, 3 o'clock in the morning, got some suspicious activity. We could be having a cyber attack that could potentially impact this unit. What the heck are we going to do about it? Well, let's get the team on the wall. Let's go to work. Let's figure out what we're going to do to mitigate the situation and try and minimize it. So let's first start with, essentially, I'll call it the entry point for the cyber experts, for network engineers, et cetera. The first thing is I better have sort of environmental and connectivity context. All right? What are the network maps? What are the inventory? What traffic is taking place? What vulnerabilities exist out there that could potentially be exploited? That's the basic context that I need. Okay? And that red box you see there on the lower right, that would be potentially a computer that is connected to, in this case, a distributed control system. Now, going deeper, understanding what that distributed control system is, once you get to that distributed control system, you start to run into a whole bunch of things that run the process that are potentially do not even have an IP address, especially for older DCS systems, different types of network things. They can receive information from your basic computers, your engineering stations, and everything else. More on that here in a minute. But you get to a whole bunch of things down there, which is where you actually control that process of your controlled bomb to make sure it's not going to explode, that if you do the wrong things down there, really bad things happen. So what I'm kind of showing you here is now we're down in the control system, and you got controllers and I/O cards and all the stuff that is down there that's actually running the process. But, someone has made a change to the configuration of one of these things that are down there. So what is it? And what do we do about it? Well, this is really, really where the control engineer is going to be critical to understanding what the change is, do I care, and do we do something about it? I know this is kind of like a bunch of spaghetti, but let me explain what you're looking at. This is a graphical representation of the control strategy for a flow controller. Maybe it's the inlet into the, whether it be the fuel or whether it be the input to the furnace that we just talked about. It begins on the left with the transmitters. In this case, there's a, might be a Rosemont, whatever transmitter. And then it feeds into an I/O card that goes into basically the basic fundamental of the control, a flow controller that's based inside the DCS system and the control logic block that makes it work. It has lots of other inputs and outputs as well. On the right, in the one thing at level 2, this may be feeding information to a historian for used for it, but on the lower right, that is connection into an advanced process control system. That thing has read-write capabilities. It wants to know, hey, what the process is, and it sends a signal back out to that thing called FC0001 to tell it, do what I want to do because I'm trying to make more product. That's a great avenue to make changes, to make really bad things happen that I don't want. Other things I can make changes in other things as well, but I'm just showing an example of the level of complexity you get to when you get down to it. It's not just as simple as, there's a block down there doing something. This stuff gets complex and meaty and nasty. That control engineer better have this information in real time. What am I going to do? What am I going to do about it? And I suggest that this is why you need this multifunctional team. When we get down to this layer, the control engineer is going to be invaluable as we respond at 3 o'clock in the morning. What are we going to do about it? But, oh my gosh, there was a change made, and it gets down into the really nitty-gritty. So we're looking now at a subset of the configuration of the logic that decides what that control valve is going to do. And in this case, this is a change made to the gain setting. Basically what gain setting is basically if I want to respond, open the valve up really far or really short, depending upon the command, is the best way I can describe it. By changing that, I can have a dramatic effect on the flow that's going to go through that furnace, whether it's the fuel or whether it is the feed. The old value was 0.41 and the new value was 0.7. By making that change and potentially some other changes, maybe to alarm settings, I can start to affect that flow I talked about going into the tube, which is the coolant that ultimately can lead to a failure. Now, the scenario that I just ran you through, I can't cite a cyber attacker for it, that someone has had this level of knowledge. But I can cite several incidents where this stuff actually led to explosions. Okay? Control problems that actually led to explosions in ethylene furnaces. Okay? But the point that I'm trying to make is that our adversaries are getting smart. If you look at some recent attacks, whether it be in Ukraine and everything else, the first thing they figured out was infiltration, how to get in. The next thing they figured out is, What are these devices down there? Before, they were just like big, giant black boxes. They had no idea what the thing was, and they've been figuring that out. The third thing they've learned is process context. What is down below there? You hear stories of they've brought in chemical engineers to understand the process underneath and what to go get if they want to go get it. Okay? So in order to meet that attack, we better have the right people on the wall that can respond and give them all the tools they need to do so. Because ultimately, if my intent is to do damage, cause physical harm, I'm probably going to change the configuration or the logic or the brains that drives the process. So, what can we conclude? Well, I hope we all agree, and you're here today, critical infrastructure is a target. If it wasn't, we wouldn't be here. We'd be at the history conference that I guess I'm late for a little bit later. You will be attacked. It is inevitable. It's not a matter of if, it is a matter of when. The question is, because they are overextended and vulnerable. This is a risk game. We must be able to reduce risk. We are never going to take risk to zero. The processes underneath are hazardous. The systems have computer chips. They are accessible. You have to improve or make sure that as a part of your incident response team, you have deep forensic analysis of configuration changes, and ultimately, with trusted restore points, have the ability to recover as quickly as you can. At the end of the day, if I'm an owner-operator and I'm operating plant, my demand of the security team is not prevent all attacks. My demand would be is if something bad happens, we can go on the news and say that I'm really sorry, we've taken the proper steps, and we'll be back online within 3 days or 4 days or whatever the case may be. That's probably the best that we can get to from a risk perspective. Okay? So that's really it for I had my conversation today. Before I conclude, I want to open it up. Does anyone have any questions or thoughts or comments? Yes, sir, David.
Hi, Mark. Dave Hickleramis. I just have a general question. I sincerely accept your point about having a control engineer in your cyber response team. But in general practice, beyond the trusted restore point, there's probably a startup sequence pre-programmed.
Yep.
And even probably a specialized safety shutdown sequence where appropriate.
Yep.
So do you need a process engineer in that room too?
Yeah, I mean, I probably should have, I could have said process/control engineer. They're certainly going to be required, right? And at some places, they're one and the same. In some places, it's two different functions, right? So I kind of use those words interchangeably, and it may end up being two people. Yes, I completely agree. Yes, sir.
I hate to say this, but more of a comment than a question, I guess. Were you aware of the work that Mike Asante, our dear departed friend, wrote on the comparison between critical infrastructure and Rome?
I know the work he's done. Actually, I did not know that. So if I stole it, then I apologize in advance for what I have done.
No, it was quite different. But if anybody else is interested, in 2008, I think it was, the late Mike Asante wrote a fabulous paper that compared the strength of the Roman aqueduct system to modern OT cybersecurity.
Okay, gotcha. No, I hadn't heard. So I'm glad I didn't steal.
No, it's all good.
Okay. Any others? Well, we will have a cabana over here. I guess we're starting over there in 30 minutes. If you'd like to talk some more, I'd welcome the chance, and I will even buy you a beer over there, or Dale will, one of the two, I don't know. Okay, thank you very much. Appreciate your time.